Hello everybody, this is paper 1 from May 2023. This is time zone 2. Let's have a look and see what we can do. Alright, question 1 is a 5-mark question. Zaha is designing a bridge to cross a river. She believes that the weight of the steel needed for this bridge is approximately 53,632,000 kilograms. The exact weight of the steel needed for the bridge is 55,625,000 kilograms. Find the percentage error in Zaha's approximation. So for this question, we're given an approximate value, some estimate, and an exact value right here. And percentage error, remember, is given to us in the formula booklet. Percentage error is given by estimate minus exact over our exact value, and then we want to represent this as a percentage. So in the formula booklet, this is under topic number 1, number in algebra. And if we go down here, 1.6 percentage error. Percentage error is equal to estimate minus exact over exact, and then we want to represent this as a percentage. So the percentage difference, the percentage in which we deviate from our exact value. So let's go ahead and write that here. Write it out in words, and then we'll input those values. So here we are. Percentage error is the estimate minus the exact over the exact value, and then we want to represent this as a percentage. And these long lines right here are absolute values. I should put an equal sign there. These long lines here are absolute values, and what that means is we don't want any negatives. No negatives. That's what that's saying. So let's write out our percentage error for these values. Our estimate was 53,632,000. Our exact was 55,625,000. And we'll write this out over our exact value. Lastly, we want to represent this as a percentage, so at the very end we'll multiply by 100. Okay, let's go to the calculator screen and work this out. Let's go into the calculator. Let's set up a fraction. 53,632,000 minus 55,625,000, and then we'll put this over our exact value, 625,000. All right, and this is giving us a value that is a fraction. That's not particularly useful. Let's go ahead and look at number, and we'll ask to convert this to a decimal. So remember, it's a negative. We don't want a negative, so we'll just take the magnitude, that is to say, the non-negative value of this. But first, of course, we need to multiply by 100 to write this out as a percentage. So initially, we had 0.0358. As a percentage, that's going to be 3.58%. And once again, we don't want this negative value. The absolute value signs around our original percentage error saying no negatives allowed. Okay, so let's write this out. Percentage error is equal to, and then we'll write this out as 3.58% to 3 sig figs. So once again, no negatives. All right. Zaha's design is used to build 5 identical bridges. Find the weight of the steel needed for these 5 bridges to 3 significant figures. So what they're testing here is an ability to round, and then also familiarity with 3 significant figures and what that means. So let's go ahead and work this out. So the exact value of the bridge, this is part A. Let's write out part B right here. The exact weight of one of these bridges is 55,625,000, and what we want is we want to build 5 identical bridges. So actually, let's go back to the calculator and work this out. Here we go. 55,625,000, and then let's times this by 5. Okay, so we have is 278,125,000. So let's write that out going back to the calculator, sorry, going back to the document here, this is going to equal is 278,125,000. And to 3 significant figures, we're only going to want to have 3 meaningful digits. And so in that case, it's just going to be these first 3. So we'll have 278 million, and then I guess we could put kilograms. Significant figures, remember, are, for example, if we're looking at with zeros, so if we have something like 0.302, this would be 1, 2, 3 significant figures. But if we have something like this would be 1, 2, 3 significant figures. And then lastly, if we had something like this would still be 1, 2, 3 significant figures. So if we have a decimal, in this case we don't, but if we have a decimal, our first meaningful digit comes with some non-zero numerical value, and then everything that follows it, even if it is a 0, is meaningful. And so as soon as we have some meaningful digit, some non-zero numerical value, everything after it is now a significant digit. So 2, 7, 8, and then of course we can't help but write anything but a 0 here, so in this case we have 3 significant figures. So this is our 3 sig figs. Okay. Part 2 of B asks us to write down our answer to part 1 in the form of a times 10 to the k, where a is between 1 and 10. So a is greater than or equal to 1 or less than 10. It's essentially a 1-digit number. And then this k is an element of, this is called our integer values. So these are whole numbers. Whole numbers are positive, negative whole numbers. So here is our original value, 278,000,000. What we want to do is we want to represent this as some multiple of 10. So in this case, we can write this as 2.78 times 10 to the, and this question is really like how many zeros do we need to have? And so we can actually begin by putting this decimal place here and then counting the number of zeros that we would need, the number of times we would need to multiply by 10 to get to the end. So if we're at this point 2.78, so we'd have 1, 2, 3, 4, 5, 6, 7, whoops. 1, 2, 3, 4, 5, 6, 7, 8 hops. So we would write this as 2.78 times 10 to the 8. And this is telling us that we want 8 zeros, essentially. 8 zeros after our decimal point. There it is, in scientific notation. 2.78 times 10 to the 8. Okay. And writing out in 3 significant figures is pretty important. It's at the beginning of the rubric, sometimes unnoticed. It says, unless otherwise stated in the question, all numerical answers should be given exactly. So for example, like root 2 or 1/2 and so on, or correct to 3 significant figures. So it's something that is important throughout the exam. Okay, question 2, 6 marks. Angel has $520 in his savings account. Angel considers investing the money for 5 years with a bank. The bank offers an annual interest rate of 1.2%, and it's compounded quarterly. Quarterly means 4 times per year. 4 times per year. Part A asks us to calculate the amount of money Angel would have at the end of 5 years with the bank. Give your answer correct to 2 decimal places. So these little things are important because they can potentially add up. For a 3-mark question, the idea that you could lose 1 mark just not having the correct number of digits, even if you understand it and get the procedure all correct. So these things are careful and sometimes shows the importance of close reading. So let's see what we can do. 520 is our initial value, and we have it in for 5 years. Let's go and look at the financial solver for 1 sec. So I'm just going to bring up the calculator screen. There's 2 ways to do this, of course. One way is the financial solver, and the other way is just going to be using our compound interest formula. So here's our finance solver. I'm just going to use this to write out each of these values on the page. So we have N, I, PV, our present value, payments, number of payments we're making per year, the final value, and then we have payments per year. So a payment is the amount, the size of the payments we're making. CPY is compounding periods per year, and then the very last one is payment at. So when are the payments being made? Okay. So let's go ahead and work this out using the financial solver, and then we'll use the compound interest formula. All right. So interest rate is always the most straightforward one to put in. In this case, it's 1.2%. Angel has $520 in his savings account. So this is $520. We imagine this money is no longer in Angel's possession or this individual's possession. It is now out of his hands. So in some sense, we write money flowing out, money flowing in. So this is 520 no longer in his hands. The payment in this case is 0. It's just he's not making any continuous payments. If it's just one payment, how many continuous payments is he making? He's not making any. Final value is what we want to find out. And in this case, our compounding periods, we're going to compound quarterly. And generally speaking, if we're not making any payments, our PPY should be the same as our CPY. And this can potentially be a little confusing, and it's actually maybe not a bad reason where for simple compound interest, it's often better to use a formula. But let's work this out just using the finance solver first, and then can use it out. We can find it using the compound interest formula later. Payment is at the end. I don't know if it explicitly states that, but banks would pay their interest at the end of the month, not at the beginning. Lastly, we have PPY relates to this N. And in this case, 4 payments per year times 5 years. So 5 times 4, there are 20 payments. And this is essentially the banks giving us 20 installments of interest over this 5-year period. So over 5 years, they're going to give us interest 4 times every year, total of 20 interest payments. So let's go and write this into the calculator and get our results. So 20 payments, 1.2, present value, money flowing out. It's not making any payments. The final value is what we're interested in, so let's leave that empty. Payments per year and compounding period for year. We'll keep these as the same in this case. If we're not making any payments and we're just looking for compound interest, keep PPY and CPY the same. All right, final value, $552 and 1.054 after that. So they asked us the 2 decimal places. We'll have to be mindful of that. So 552.11 in this case. All right, let's go back to the document and write this out. So final value, can use a different color, I suppose. Actually, let's just write it out here. This is what we were trying to find. Therefore, our final value is equal to $552.11 to 2 decimal places. Okay. The other way to do this, because this CPY and PPY can sometimes be a little confusing, and for a 3-mark question, 1 mistake on the financial solver would just lead to potentially 0 marks or potentially just 1 mark. And so it's a little risky, potentially. There's a lot that could go wrong. Not getting N, for example, or with this CPY and PPY being different, or if you forget to put end. Potentially a lot could go wrong. So let's go to the formula booklet and let's look at compound interest. So if there's no payments being made, no constant payments being made, we can just use our compound interest formula. And here it is. This is our compound interest formula. Present value is equal to, final value is equal to present value times 1 plus R, our interest rate, K, number of compounding periods per year, and N, the total number of years we have this investment in a bank. So let's write that out. To be honest, I think this is actually the easier way. So here's the alternate method. Final value present value 1 plus our interest rate over 100 times compounding periods per year times number of years in the account, again by compounding. So let's write this out. Here's $520. We're going to multiply this by 1 plus interest rate 100 times compounding for 4 times a year. It's in for 5 years, and then we'll multiply this by 4 once again for that total of 20 payments essentially. Okay, let's work this out on the calculator. 520 times 1 plus 1.2, 100 times 4, and then we'll raise this to the power of 5 times 4, or 20 if we wanted. And there it is once again, $502 and 10.5 cents, or 11 cents. Okay, and to be honest, I think that's the easier way. I'd recommend that way. I think it's less prone to errors. Okay, let's go back to the document. Instead of investing the money, Angel decides to buy a phone that costs $520. At the end of 5 years, the phone will have a value of $30. It may be assumed that the depreciation rate per year is constant. Calculate the annual depreciation rate of the phone. Okay, so once again, we can actually use our compound interest formula, or we can use the financial solver. And this time I'm going to actually reverse the order. Let's get a clean line here, and we'll start on question B. So here's A, here's B. So let's reverse the order and write out final value, present value. We'll use our compound interest formula. So in this case, we have $30 at the end. The final value is equal to 30. The present value of the phone was equal to $520. 1 plus, and in this case, we want to know the value of R, the depreciation rate. So that's our unknown. 100 times, in this case, the depreciation rate per year is constant. So it's not like we have any kind of compounding or any kind of fractional compounding per year. So in this case, we're actually just going to divide our interest rate by 100, and we're not even going to need any k value. And then n, the number of years, is 5. After that, we can go ahead. We've got some equation just in terms of r, one variable, so we can go ahead and n solve. I'm just thinking about this now. Often exponential equations are a little funny in n-solve, so I'm a little unsure whether the calculator will accept this. So let's go to the calculator and try to work it out. Menu, algebra, numerical solve. 30 is equal to 520 multiplied by 1 plus, and in this case, we have r over 100. We want to raise this to the power of 5. And let's ask the calculator to solve for r. And in this case, it worked out okay. So this negative depreciation rate means that our interest rate is now not increasing. The value of this phone doesn't increase through time, but it is negative. It depreciates, rather. So we have negative 43.47, or 43.5%. That's the value that the phone loses every single year. So let's go back to the document and write this out. So in this case, R is equal to the annual depreciation rate, and the annual depreciation rate is, what was it once again? 43.5%. And that should do it. If you want to work this out using the compound interest formula, we certainly can. Or sorry, not the compound interest formula, but the financial solver. We certainly can, and I'll show you how to do that really quick, or as quick as possible. So alternate method, here we go. N-I, PV, PMT, final value, payments per year, compounding periods per year, and then payment at the end. We'll leave that empty because we don't need that in this case. But it's always at the end. So in this case, the interest rate is what we're trying to find, the depreciation rate. The present value is going to be the value of the phone. And in this case, we'll still put negative 520. In this sense, the value is locked up in a phone. And I think, to be honest, we could actually switch the values. We could put this as positive, and our final value would be negative. Or in this case, we can just imagine it's 520 values. But our final value is $30. So we can imagine that, in this case, the logic is this. We have this $520 locked up in the phone, and at the end we are going to sell it, or the value that we have available to us at the end is going to be $30. I'll show you what happens if we were to put positive, positive. The calculator would just give you an error, and that's usually just a signal that this present value and final value you want to keep different. Okay, payment is going to be 0. PPY, CPY, we'll just leave this as 1. What essentially we're saying is that the depreciation rate, which we already know is 43.5%, happens every year. That is to say, 43.5%. This phone loses 43.5% of its value every year. And number of years is just 5. Remember, these two things are related. So PPY 1 times 5. And that should be it. Okay, let's type that in, and I'll show you the error that you get potentially if you were to try to work it out and forget the signs. So n is 5. Let's imagine that this is 520. Payment is still 0, and the final value is 30. So the interest rate is what we're trying to find here. PPY is 1, and CPY is also 1. Payment at the end, this is good. So if you were to type this in on your calculator and keep this present value and final value the same, you would get no sign change, which means that essentially the calculator is telling you that it's not possible. You can't go from 520 to 30 because, well, what I believe the calculator is understanding is that if you have this in your possession, it can't go from 520 to 30 with any kind of interest change. There's nothing we can multiply this by. But if we change the sign to negative 520, then it will give us our depreciation rate, or the change in the value of the phone every single year, which is 43.5% once again. So whenever you get that no sign change, often due to this present value and final value being different. Okay. Let's go back to the document and continue on. Okay, in a school, 200 students solved a problem in a mathematics competition. Their times to solve the problem were recorded, and the following cumulative frequency graph was produced. So here we have it. 200 total students taking part, and then we have the time that they took to complete this mathematics competition. Using the graph, now we have median, lower quartile, upper quartile, interquartile range. And then it looks at the very end that we're asked to determine if a particular score is an outlier. So pretty common question, actually. Let's go work this out. So use the graph to find the median time. Median, we know, is the middle value. So if we have 200 students and they all took a different time to complete this test, the median would be the 100th student. The student is above half and also below half. The middle value, if you were to rank them all and line them all up. So let's find, in this case, I mean, mathematically, we have 200 times what is the half of this, and we're looking for the 100th value. So let's go. Sometimes on the mark scheme, the margin for error is pretty small, so I'd encourage you to use a ruler, almost certainly. Okay, so let's see what this value is for the median. This would be 35, 6, 7, 8. Median time is 38. Lower quartile, remember, is going to be the 25th percentile. Lower quartile. So if we have a box and whisker plot, dividing it up into quartiles, lower quartile 25%, median 50%, upper quartile 75%, and so on. So this would be 0.25 times 200. We're looking for the 50th value in this instance. All right, there we go. And so this would be Q1. This would be 32. Upper quartile, 200 times, and this would be 75th percentile, which is going to give us 150. Okay, and this is Q3 right here, and this is, looks like 42 in this case. 42, interquartile range, IQR is equal to Q3 minus Q1. I believe this is actually given to us in the formula booklet. So this is Q1 right here. And this is, of course, Q3. So we have 42 minus 32, or IQR, is equal to 10 seconds. So what that means is that 50% of the students took 50% of the students has this range where they took between 10 seconds in this case, or took between 32 seconds and 42 seconds. That's our IQR. Cedric took 14 seconds to solve the problem. Determine whether Cedric's time is an outlier. Okay, so we have a formula for our, actually no, we don't have a formula for outliers. Not given to us in the formula booklet at least. So what is an outlier? If we have, for example, our box and whisker plot right here, and we have these values of, let's say, what is this? This is going to be 38. This is 32. This is 42. And so we have values for Q1, our median, and Q3. The question is, if we have some value, which in this case is at 14 seconds, so all the way, for example, down here, I'll write it out in a different color maybe, all the way down here, the question is, are the whiskers themselves going to extend to that point? So it's possible to have some values above, and the whiskers may extend, and it's possible that, we'll have some values below, marking this bottom 25%, for example. But the question is, does it extend all the way to this very, very low point of 14 seconds? And to do that, we have a formula, which is, how do we tell if something's an outlier? If it is 1.5 times IQR, our interquartile range, let's say below or above Q3, above Q3, or below Q1. So essentially, these whiskers themselves are only going to extend 1.5 times the IQR. So here we go. 1.5 times the IQR below, in this case, Q132. So 1.5 times IQR of 10 is equal to 15. So with Q3, so we have Q3 minus 1.5 times IQR is going to be 32 minus 1.5 times IQR is equal to 15. I'll write that out actually once again. 1.5 times 15, 32 minus 15 gives us a value of 17. So 17 is the extent to which these whiskers will travel. This is the lowest point they'll go, and we know that Cedric's score right here is 15. And so is Cedric's score an outlier? Yes. Yes, it is. Yes. Determine whether Cedric's score is an outlier. Yes. Why? Because 14 is less than 17, our minimum bound. I realize we're at 14 here. 15 rather. So here we go. So since this value of 14 is less than our lowest possibility of 17, it is an outlier. It lies too far beyond the main cluster. Okay. Let's go on to question 4. At a running club, Sun Jin conducts a test to determine if there is any association between an athlete's age and their best time taken to run 100 meters. 8 athletes are chosen at random, and their details are shown below. So we have different athletes from A to H, or 8 total athletes. We have their age and the time it took them to run the 100 meters. Sun Jin decides to calculate the Spearman's rank correlation coefficient for his set of data. Complete the table of ranks. So let's look at the time rank first, just because they give us the value of 1, and that should usually give us some kind of indication of how they want us to rank these values. So we see 1 corresponds to the longest time, and so let's go from longest to shortest. One other thing, 2-mark question. There's only 2 rows, so it suggests that there's going to be no ties, for example, and we're just looking for straightforward rankings. So from highest to lowest, this would be 1, 2. Actually, sorry, after saying that, there is actually a tie right away. So we see these 2 values, 13.4, 13.4, and they both can't take the 3rd position. They both can't take the 4th position. So what we do is they share the 3rd, 4th position. We average this out, and they both share 3.5. So this would be 3.5, and this would be 3.5 as well. So here's the 1st, 2nd, and then this is the 3rd, 4th, where they share this position. And after that, we would continue on, and this person number H, would be the 5th longest, or had taken the 5th longest time. This would be 6, 7, and 8. Okay, so for ranking these from longest time to shortest, let's rank the age from oldest to youngest as well. So this would be the oldest person right here, and this would be the 2nd oldest. 3rd oldest is already given. Then we have the 4th oldest, the 5th oldest, 6th oldest, 7th, and the 8th. Okay, so a little strange that it's only 2 marks. Usually there's 1 mark per column and then 1 mark for recognition that there is some kind of tie here. Alright, part B asks us to make use of this table and asks us to calculate the Spearman's rank correlation coefficient, RS. Okay, so to work this out, we're going to go into spreadsheets and run 2 variable statistics. So let's go back to the document. Here we are in the calculator spreadsheets. Let's label X and Y. We could put A and T, age, time, but doesn't matter so much in this case. Let's put our values in. In this case, to find Spearman's correlation coefficient, what we do is we put the rankings in, and we calculate this correlation coefficient just as we would Pearson's, but instead of putting the actual values, we put in the rankings. So this is athlete A, they were the 7th, athlete B was the 6th, athlete C was the 3rd oldest, and so on and so on and so on. And so we put our rankings in, and then we match the coordinate pairs. So if this was the 7th athlete, or athlete A was the 7th oldest, the 7 matches up with 3.5, 6 matches up with 2, 3 matches up with 3.5. This athlete D, for example, who was the 5th oldest, took the 6th longest, and so on and so on. 1 and 5. Alright, so let's go ahead and statistics, stat calculations, and in this case we wanted to 2 variable statistics. We're comparing these 2 variables of age and time. So we put X within our X, Y within Y, that's all we need. And here we're going to look for R, our correlation coefficient. And there it is. Negative 0.6706 or 0.671, negative 0.671. So let's go back to the document and write this out. RS is equal to negative 0.671 to 3 sig figs. Okay. C, interpret this value of RS in the context of the question. So whenever they write context, even though it's still just a 1-mark question, they're looking for specific mention of these variables. So in this case, we can say there is a negative correlation or there is a negative association. There is we can say, a moderate negative correlation between the ranks between, let's say, age and an athlete's time to complete 100 meters. 100-meter sprint. Okay. Part D. Let's go on. 1-mark question. Suggest a mathematical reason why Sung-Jin may have decided not to use Pearson's product moment correlation coefficient with his data from the original table. So why he did not want to use Pearson's. So remember, Pearson looks for linear correlation, where Spearman just looks for an increase in one variable is associated with an increase in another variable, increase or decrease. So a few different things that we could say for part D. We could say that Spearman is less sensitive to outliers, for example, which it is. Less sensitive to outliers. The most common or most likely would be to say that perhaps relationship may not be linear, and Spearman gets around that just because it looks for what's called a monotonic relationship. That is to say, increase in one variable is an increase in another variable. Relationship may not be linear. So really maybe he's just looking to see, as age increases, does time increase? Not necessarily a linear association, but just as one increases, does the other increase? Okay, question number 5. The following frequency distribution table shows the test grades for a group of students. So here we have the grade and then the number of people that were awarded that grade. For this distribution, the mean grade is 4.5. So this is the average grade of all these students is 4.5. Write down the total number of students in terms of P. So not a bad question itself, but you need to know what it's asking. So total number of students. So these are all the students that took part. We know that 1 student got a grade of 1, 4 students got a grade of 2, 7 students got a grade of 3, 9 got a grade of 4, and so on. And then this is the total if we add it all up. And we don't know all of the values because we don't know P, so we therefore would write this in terms of P. So our total number of students is going to be equal to 1 plus 4 plus 7 plus 9 plus P plus 9 plus 4, which, if we were to add that up, I'm actually just going to use my calculator here. 7 plus 9 plus 9 plus 4 is just going to be 34 plus P. So we add up all the numerical values, and P is not something we can really integrate with all the numerical values. So we have 34 students plus this unknown value of P, and that would give us our total number of students. So total number of students in terms of P is just 34 plus some unknown value of students that got a score of 5. Here they ask us to calculate the value of P. So the value of P, and in this case we're going to look for an equation. They told us earlier that the mean grade was 4.5. The question is, how can we create an equation to incorporate that and then solve for P? So let's go ahead and see if we can work that out. So what do we know? The mean itself is equal to the sum of all values over the total number of values. Total number of values, in this case the total number of students. So we know the mean. We know the mean itself is equal to 4.5. That is to say the average grade is 4.5. And the sum of all values. So if we add up everyone's grades and then divide by the total number of students, we'll be able to find the average grade in the class. So we know that one person got a grade of 1, 2 people got a grade of 4, 3 people, I'm sorry, let me go back. So we know that, let's go this way. One person got a grade of 1, 4 people got a grade of 2, 7 people got a grade of 3, 9 people got a grade of 4, P people, some unknown value, got a grade of 5, 9 people got a grade of 6, and 4 people got a grade of 7. So that looks about right. And the total number of students that took part was what we were asked to solve at the very beginning. This is 34 students plus some other number of students. So the total number of students is given by 34 plus P, some unknown. And now we've got an equation where we just have one unknown right here in the top and the bottom, in the numerator and denominator. And so what we can do is we can end solve this. End solve for P. Okay, so kind of lengthy here, but let's go ahead and work this out. Let's go back to the document, just clear this. All right, so let's go into menu, oops, algebra, numerical solve. 4.5, that's our mean, is equal to, we're going to need to set up a fraction. Might not be a bad idea to actually work out the numerical values first and then add it later. Just because there's so much to type in, I'd be cautious about double checking as well, making sure that everything is okay. And we'll put P here. Plus 9 students who received a grade of 6, plus 4 students who received a grade of 7. All right, and then we have at the bottom 34 students, total number of students, which is represented by 34 plus P. That's a calculator to solve for P. All right, function is not defined. Let's see what went wrong. Plus 5 times P. Okay. Let's see, sometimes this is due to the multiplication and brackets right here. There we are. So just be mindful. Okay, so P is equal to 10. What that tells us, there were 10 students that got a grade of 5. So let's go back to the document. Calculate the value of P. P is equal to 10. And what's good about that, and what should be reassuring, is first off, it's not a fractional value. So it's not like 10.5 students. And second of all, it looks to be within the range of these other, it's not like 46 or something like that. So that should be pretty reassuring as well. Okay, question 6. A company that owns many restaurants wants to determine if there are differences in the quality of the food cooked for 3 different meals, breakfast, lunch, and dinner. Their quality assurance team randomly selects 500 items of food to inspect. The quality of this food is classified as perfect, satisfactory, or poor. The data is summarized in the following table. So here we have the quality, here we have the meals for breakfast, lunch, dinner, and then we have the different ratings, of course, as perfect, satisfactory, or poor. And then we have the totals along here. Okay, an item of food is chosen at random from these 500. Find the probability that its quality is not perfect given that it is from breakfast. Okay, so given that is a big hint that we're dealing with conditional probability, and when we're dealing with conditional probability, we're dealing with a subset of our total sample. So often the case, we should read these from back to front. So we've got 500 pieces of fruit, given that it's from breakfast. So here we are looking at our breakfast right here. Given that we sampled something from our breakfast menu, I suppose. Given that we've sampled something from breakfast menu, given that we're dealing with these 232, let's say, breakfast options that were selected, what is the probability that it was not perfect? So given that it was selected from the breakfast portion, what is the probability that it's not perfect? So we're dealing with this subset right here. Should use the calculator. Sorry, this highlighter right here. Given that it was not perfect, and that's actually kind of interesting because this is perfect, this is not perfect, and this is not perfect. So it's either satisfactory or poor. That's the total number of ways in which it could be not perfect. Okay, so that's not a bad question. And then this will be 131 over 232. 31 over 232. And this gives us a value of 0.5647 or 0.565. Okay, so once again, given that it's from breakfast, given that we're dealing with these 232 items, out of these 232 items that we have before us, what is the probability that one of these was not perfect? And so we know 100 out of the 232 were perfect. And so the remainder right here were not perfect. Good question. Good question. Okay. A chi-squared test at the 5% significant level is carried out to determine if there is significant evidence of a difference in the quality of the food cooked for the 3 meals. The critical value for this test is 9.488. The hypotheses for this test are: null hypothesis, the quality of the food and the type of meal are independent. The quality of the food and the type of the meal are not independent. That's for the alternative. So we've got this chi-squared test, chi-squared independence test. Significance level is 5%, and we've got a critical value for the chi-squared test being 9.488. So this isn't the p-value, this is the chi-squared value. And we want to see if these meals, that is to say, the quality and the meal are independent or, let's say, not independent. So find a chi-squared test statistic. Okay, so for this, we're going to go into the calculator and we're going to need to create a matrix. So let's go create a matrix. And it's a 3x3 matrix. So we don't include the totals in this case, just perfect, satisfactory, poor, breakfast, lunch, dinner. And let's put in the values 101, 124, 7, and so on. So these are just straight from the table itself, and of course not including the totals. We don't include the totals. Alright, after we have the matrix, let's define it. Control var. Let's define it as A. Alright, and then we're going to go into statistics, stat calculations, statistical tests, and we're going to do a chi-squared two-way test. So not a goodness of fit, but a two-way test. Our observed matrix is in A, and there we go. So there's our chi-squared value, there's our p-value, and our degrees of freedom, and so on. Alright, let's work out B. Our chi-squared value is equal to 11.02, so just 11.0. And let's write out the p-value as well. P-value is equal to 0.0263 or 2.63%. Okay. State with justification the conclusion of the test. So we've got a chi-squared value and a p-value, so we can use either one since we have a significance level and a chi-squared. P-value is the most common, so let's actually just start with that. So what can we say? Let's relate our p-value to p-critical. What is that? We know that 2.63% is less than 5%, and so our p-value is less than our critical value. In this case, we would reject the null hypothesis. You can think of this p-value right here, 2.63, as the probability that our null hypothesis is true. And there's only a 2.63%. That's very small, and it's less than our cutoff point. So 2.63%, we would reject the null hypothesis. State with justification the conclusion for the test. So this would be our justification, and this would be conclusion. If we wanted to write this out in context, we would say the quality of the food and the type of meal are not independent. All right. Last one, I guess we can show you the other way. We can say our chi-squared critical value is greater than 9.488. So our observed chi-squared value, is larger than our critical value. Chi-squared value measures the difference between the observed and the expected. We see we have a larger difference between the observed and the expected than, in some sense, we're willing to tolerate. So we see this large deviation from what we observe and what we would expect just based on chance. And so there seems to be something more going on in this relationship, and that's why we would again reject the null hypothesis. Okay. Part 7. Annie owns 4 cafes represented by points A, B, C, and D. Annie wants to divide the area into delivery regions. This process has been started in the following incomplete Voronoi diagram, where 1 unit represents 1 kilometer. The midpoint of CD is 5.5, 1.5. So the midpoint of CD right here is 5.5, 1.5. Show that the equation of the perpendicular bisector of CD is y equals negative 3x plus 18. So let's go ahead and draw a line between, I'll use a different color, the line between C and D. We want to find the perpendicular bisector, that is to say the line running through in this case. Perpendicular means, of course, that it's going to intersect at a right angle. We know one point on this line already is 5.5 and 1.5. That's the midpoint. And this midpoint is also going to be critical because our perpendicular bisector is going to run through this point. And if we know one point on the line, all that's left is us to find the slope and the y-intercept using this point. So let's go ahead and work that out. So equation of perpendicular bisector of CD is y is equal to negative 3x plus 18. So let's work this out here. So equation of a line is given by y is equal to mx plus b. Let's find the slope and the y-intercept. Given that we have this perpendicular bisector right here, we know it's perpendicular to this line CD. So let's find the slope of this line CD. So let's say m of CD, just to say the slope of CD. Slope equation is given to us in the formula booklet. I'm going to write it out here. It's y2 minus y1 over x2 minus x1. And so we know point C right here is 7, 2. And we know point D is 4, 1. And if we want, we can put some values of x1, y1, just to simplify things. And we can call this x2, y2 if we want. Okay. And so, hopefully it's still possible to see everything. I'm just going to continue on here actually. So y2 minus y1 over x2 minus x1. And of course it doesn't really matter the order. We could have easily called this x2 and y2, and we could have called these ones x1 and y1. As long as you're consistent, the order actually doesn't matter. y2 minus y1 and x2 minus x1. So we'll have negative 1 over negative 3 or 1 over 3. You can put this into your calculator, of course, as well. Alright, so if we know that MCD, the slope of this line segment right here that connects C and D, is equal to 1/3, and we're looking for the slope of this line right here, the perpendicular bisector to CD, this one again right here, we know it's going to be perpendicular. So let me actually just simplify this a little. We know that M, we have some M, and it's equal to 1/3. M perpendicular is of course just going to be the top and the bottom rearranged, 3 over 1, and then of course multiplied by a negative. And so our perpendicular line has a slope of negative 3. So y is equal to mx plus b, negative 3x plus b. And now we just need to find our y-intercept. We have 3 unknowns, x, y, and b. But the thing is, we do know one of these points on the line. We do have an x value and a y value that is on the line. So we should be able to substitute. We have this value right here, where x is equal to 5.5 and y is equal to 1.5. So let's substitute that. So y is equal to 1.5 when x is equal to 5.5 plus b. So we've got 1 point on the line, and that's our midpoint. Let's go ahead and solve for b. Actually, what I'm going to do, I'm going to work this out on the calculator. Negative 3 times 5.5 plus 1.5, and it would give us a value b is equal to 18 in this case. So you can work it out through algebra, or you can end solve. So altogether, our equation of a line is y is equal to negative 3x plus 18. And I forgot what it said up here. There it is, negative 3x plus 18. Okay, good. Complete the Voronoi diagram shown above. Actually, sorry, one last comment. For a 3-mark question, chances are they'll want to see calculation of the slope. So gradient formula, calculation of slope, conversion to perpendicular, and then you'll have a value of b, or simply just our total equation. We're finding the value of b, we know it matches up with this equation. Okay. Complete the Voronoi diagram shown above. Okay. Going to erase this here, and then we can continue on. So Voronoi diagram, what does it do? Let's take one point, for example, right here, this point B, and we see B has these bounds, these boundary lines which enclose it. And what that means is that every single point within this range is closer to B than any other point. This boundary line marks the dividing line where upon either side something is either closer to B or closer to C. At these points we're an equal distance away from BC. These points were an equal distance away from C and D, and so on. So we've got most of our boundary lines already written in, but there's one that isn't. And that is, of course, the boundary line between A and D. This is to say, we have D and C, we have B and C, we have B and D, but we don't have this boundary line here. So let's find that out. Coordinate point of A is at 1, 1, and coordinate point of D is at 4, 1. We know that the boundary line is a line which is equidistance from both points. That is to say, this boundary line right here is an equal distance between B and C, and the midpoint, for example, was between D and C. Since these have the same y value, they both have a y value of 1, our boundary line is just going to be halfway through here, and it's just going to be a vertical line. So we can find the midpoint, and the midpoint formula is just given by this. Midpoint is equal to x1 plus x2 over 2, and then y1 plus y2 over 2. And in this case, we have 1 plus 4 over 2, and that's actually all we're going to need in this case. And then this is going to be 1 plus 1 over 2. So our midpoint is going to be 5 over 2, or 2.5, and this is just going to be 1. And this is the x value that we're concerned with. So this point right here, where x is equal to 2.5. So complete the Voronoi diagram shown above. We just have this line 2.5, and I think I actually extended a little too far, only going up to there. So we have this dividing line right here between A and D. Since they have the same y values, we're just looking for some x value between, and then it's the vertical line. Vertical lines, of course, just have an equation where x is equal to wherever that line is placed. Alright, Annie opens an office equidistant from 3 of the cafes B, C, and D. So some point in equal distance between B, C, and D. The equation of the perpendicular bisector of BC, that's this line right here, is 3y equals 2x minus 1.5. Find the coordinates of the office. Okay. So earlier they gave us the perpendicular bisector of CD. So we know this equation. And now they're giving us an equation of another perpendicular bisector. So essentially the boundary line between B and C. And we want to know where Annie is going to open this office. That is to say, we want to know the coordinate points of this junction, in this sense, where these boundary lines meet. Because at that point we're equal distance away from both B, C, and D. So equal distance away from B, C, and D. All of these will be an equal distance. So what are the coordinates of this office? Since we have two equations, we want to see where they meet. This is an interesting question. I'll write it out over here. So we have one boundary line. We have the boundary line of CD. And I'm going to represent this as, we can represent this as f of x, or to simplify things, we can call it our equation 1. So we have y1, and that's equal to y equals negative 3x plus 18. And then we have this other equation, and we could have called it f of x and g of x if we wanted to. But we can also call it y1 and y2 to simplify things. But remember, these things actually are equivalent. So we could have said f of x function 1 and g of x and so on. It wouldn't have made a difference. So if we know y2 is given by this equation, 3y is equal to 2x minus 1.5. The question is, where does y1 equal y2? That's going to be where they meet. So this line and this line. If we can find out where they meet, then we'll be good. And so y1 is, now this is going to be somewhat tricky because y1 is already has y on one side, but y2, this second equation, is in terms of 3y. And so that makes it tricky because we can't equate them to each other, not until we, let's say, make a certain move. And I'll show you what that is. So if we're looking at the second equation right here, 3y is equal to 2x minus 1.5. And we want to get it just in terms of y. That is to say, we want to get y all by itself, so then we can set one equation equal to the other. We're going to need to get rid of this 3. What we can do is, if we don't want 3 y's, but we only want 1, we just want 1 y by itself, what we can do is we can divide everything by 3. So let's divide this by 3, divide this by 3, and divide this by 3. So 2x over 3 is going to be 2x over 3. 1.5 divided by 3. This is going to look a little kind of unorthodox, but we can do the same. Just divide everything by 3. And now we've got an equation which is just in terms of x. And then our y similarly is all by itself. And now we should be able to use this. y1 is equal to y2. Alright, so here we go. This is our y1. And it is negative 3x plus 18. And this is our other equation. It's 2x over 3 minus, and let's leave it like this. The calculator will accept it even though it looks a little funny. And now we can find our value of x. And so let's go ahead and then solve. To be honest, it's a fairly elaborate question for only 2 marks. Okay, so let's go back to the calculator. Menu, algebra, numerical solve. Negative 3x plus 18 is equal to, and we'll set up fraction of 2x, oops, 2x over 3 minus 1.5, oops, minus 1.5 over 3, and we'll ask the calculator to solve for x. So it's not a nice point, but I think partly is don't really want us to solve this just by looking at it. And so x in this case, going back to the document, x is equal to 5.04545. And to find the y value, we already have an equation in terms of x and y. So what we can do is we can substitute this x value of 5.04545 back into this equation and find the y value. So we'll go back to the calculator real quick and go ahead and do that. So negative 3, oops, here we are. Negative 3 times 5.04545, and then plus 18. And so we have 2.86. So going back to the document, y is equal to 2.8636. So we'll just leave it as 2.86. Since we're done using the x value, we saved sig figs just until the end, but now we can go ahead and round this up to 5.05, and 2.86. So that should be good, but as a coordinate point it also looks like this, 2.86. And let's see if that is about right. 5.05, 2.86. Just by inspection, it looks pretty good. One thing I was just thinking, in terms of this question, if we want to find the intersection of these two lines, we can do this idea of y1, y2, but I was just thinking of our linear equation solver here. So at the calculator right here, solve system of linear equations, 2 variables, x and y. So linear equation, if we have 2 linear equations, that means our x value isn't raised to a power of 2 or 3. It's not a quadratic, but if we just have straight lines, equations of straight lines, we can put those into our linear equation solver, and then if it's just in terms of x and y, which it usually is, we can ask the calculator to find the intersection. So this actually, for a 2-mark question, might be more efficient, and it might take less algebra. So I'm going to work it out here as well. Negative 3x plus 18. But here again, it's y is equal to negative 3x plus 18. And now we have 3y. I'm somewhat doubtful that this will work, but it's possible it will. Okay, so that was actually much, much easier. Jeez. Okay, linear equation solver, put one equation in, put the other equation in terms of x and y, and then it gave us our values just like that. So I was wondering, for a 2-mark question, it seemed pretty elaborate, but just using linear equation solver, linear equation number 1, linear equation number 2, where do they meet? So not bad, actually, not bad. Okay, let's go on to question 8. Ruhi buys a scoop of ice cream in the shape of a sphere with a radius of 3.4 centimeters. The ice cream is served in a cone, and it may be assumed that 1/5 of the volume of the ice cream is inside the cone. Okay, this is shown in the following diagram. Calculate the volume of ice cream that is not inside the cone. So not inside the cone. There's 1/5 inside the cone, and of course 1 minus 1/5 means that 4/5 is not inside the cone. Okay, so volume of the ice cream that's not inside the cone, essentially our ice cream is just as a sphere, so what we need to do is we need to calculate the volume of the sphere and then multiply it by 4/5, because 4/5 of it is not in this cone. Let's go ahead and look at the formula for the volume of a sphere. Oops, we need to get out of this. Okay, so going into geometry topic 3. Here we are. So volume of a sphere. Volume of a sphere, right here. Volume is equal to 4/3 pi r cubed. Okay, where r is the radius. Okay, so volume of a sphere is given by 4/3 pi r cubed. So 4/3 pi, and then our radius of 3.4, and then we want to cube that value. Just be careful with your order of operations as you work this out. Mindful of your brackets. We're cubing the radius and the radius only. So let's go to the calculator and work this out. So 4/3 times pi times 3.4, and let's raise that to the power of 3. So 3.4 cubed. Right, and this is our total volume, but we don't want the total volume, so let's multiply it by 4/5, because only 4/5 of this volume is outside of the cone. And so there we go, 131.709. So here we go. Let's go back to the document for a sec. So this was our total volume, 164.636, but we don't want the total volume. We wanted to multiply our volume. So we wanted to take 164.636 and we wanted to multiply it by 4/5, which gave us a value of 131.7, or to 3 sig figs, 132, in the sense cubic centimeters. Alright, so not too bad of a question. Alright, the cone has a slant height of 11 centimeters and a radius of 3 centimeters. The outside of the cone is covered with chocolate. Calculate the surface area of the cone that is covered with chocolate. Give your answer correct to the nearest centimeter. Alright, so we've got this cone right here, and there's going to be chocolate around the edge. We know the radius of the cone at its base is equal to 3 centimeters. So this might get a little small here, but we know the radius itself is equal to 3. And the cone has a slant height of 11. So what that means is if we have this radius here, the slant height is equal to 11. So going from the apex, or the tip of the cone, all the way to its base, we travel a distance of 11. Alright, we want to find the surface area of the cone, so let's go ahead and go back to the formula booklet. So, let's say, where is it? Area of the curved surface of a cone. Area is equal to pi times r times L, radius, and the slant height. So not a lot of manipulation that we need to do for this question, which is not too bad. So the surface area, this is part B, is given by pi times the radius times the slant height. Pi remains pi, the radius at the base is 3, and then the slant height is equal to 11. So that is not a bad question. Let's go, I'm actually just going to work this out on the calculator that I have beside me. So it's pi times 3 times 11. And this will give a value of 103.67. To the nearest centimeter is going to be 104 centimeters. And I'd almost wonder if there was something more to that question, just because it seemed a little straightforward, but that is it actually. That's all there is to it. Okay. So not a lot of manipulation here actually, it's just more straightforward substitution. In this case, we have 1/5 in the cone, which means 4/5 is outside of the cone. So not too bad of a question. Okay, let's continue on. Alright, question 9, 6 marks. The lengths of the seeds from a particular mango tree are approximated by a normal distribution. So already we know we're in the realm of normal distribution, norm CDF or inverse normal. And the lengths of the seeds are approximated with a mean of 4 and a standard deviation of 0.25 centimeters. A seed from this mango tree is chosen at random. Calculate the probability that the length of the seed is less than 3.7 centimeters. So remember, when we're talking about a normal distribution, we have this bell curve, and it's symmetrical, and it's centered about the mean, which in this case is 4 centimeters. And we have this standard deviation, which is a measure of spread, and they're telling us that the standard deviation is 0.25. And not super necessary in this case, but remember, for our standard deviation, we have roughly 68% within one standard deviation, and then we have 95% within 2 standard deviations. Small standard deviation tells us that we're tightly clustered about the mean. Larger standard deviation means we have something that is more spread out, data values that are further away from the mean, more like distributed further away from the mean. It would be flatter, our standard normal curve. Okay, so part A asks us to calculate the probability that the length of the seed is less than 3.7 centimeters. 2-mark question. Remember, for this, if you're not sure how to work this out, process marks at very least are a sketch. So throughout, I'm going to draw a sketch here. So calculate the probability that the length of the seed is less than 3.7 centimeters. So here's our normal curve. Here's our mean of 4. And we want to find the probability that we have a length less than 3.7. So if the area under the curve represents all of these seeds, we're looking for the percentage that is to the left of this 3.7. So less than 3.7. That's what this is. It's less than 3.7. Okay, so let's go to the calculator. Let's go menu, probability. In this case, we're in distributions, and we're going to use norm CDF. And so our lower bound, we can keep this as some massive negative value. The idea is we just want to capture all of the seeds to the left, or that are less than this value of 3.7 centimeters. Our upper bound is 3.7, so everything below 3.7, from some negative, massively negative value to 3.7. Our mean in this case is 4, and this is our standard deviation. Our standard deviation is 0.25. Just one last thing. If we're in normal distribution and they say less than, we don't have to worry about less than or less than and equal to for normal distribution. We just put a value, 3.7, this is our upper bound. Okay, let's go ahead, and we have roughly 11.5% of our seeds are less than 3.7 centimeters. So let's go ahead. This is already a method mark, so it's okay. But I'm going to go ahead and write norm CDF and then put those values in. So I'm just going to put negative 999. Essentially, we can put 0, a seed of 0 length or something like that, or slightly greater than 0. 3.7, this is 4, and 0.25. Mean, standard deviation, lower bound, upper bound. And we said that this was equal to 0.115. You can write this as a percentage if you want. Okay. Part B, it says, it is known that 30% of the seeds have a length greater than k centimeters. Find the value of k. So in this case, we're given the area under the curve, and we want to find the cutoff point. So let's go ahead and draw another sketch to see what this actually is. So we've got a normal curve once again. I'll rewrite that actually, make it a little better. Okay. Here we go. A mean of 4, and it is known that 30% of the seeds have a length greater than k. So we only want an area of 30%, and we want it to be greater than some cutoff point. So in this case, let's use red. We have some cutoff point k, some value k, and we want only 30% of the seeds to be greater than this value of k. So, okay. All right. So in the first question, we had a cutoff point, and we wanted to find the area. That was our norm CDF. Here we have the area, but we need to find the cutoff point. So if this is normal, we're going to use inverse normal here. So let's go to the calculator screen and work this out. Menu, probability, distributions, and in this case we're going to go inverse normal. So the area under the curve, actually going to go back to the document one sec and just explain something. So our calculator sweeps out from left to right. So when you give it a cutoff point and you're asked to, you're telling the calculator rather what area you want to sweep it through. If we would just put 30, the calculator sweeps from left to right, and it would actually work out this value right here. But we want the calculator to sweep through 70% so that only this 30% is remaining. So to go back to the document, sorry, the calculator rather, the area is going to be 0.70. So we're interested in the cutoff point for which 30% of the seeds are greater than this value. If the calculator sweeps from left to right, we want it to sweep through 70% of the values to reach this cutoff point. Mean once again is 4, standard deviation 0.25. Okay. And here we go, 4.1311. This is that cutoff point, the length of the seed, 4.13 centimeters, and 30% of the seeds are greater than this value. So let's go ahead and type this in. Alright, so k is equal to 4.13, and that's reassuring because it's to the right of the mean. And that would give us this 30%. This is already processed, but I'll write this out as well. Inverse normal, and then we put the area that we want to sweep through, in this case the mean and the standard deviation, and that gave us a value of 4.13. Okay. This is a nice question right here, part C. For a seed of length d centimeters chosen at random, the probability that we're within this certain range, centered about d, is equal to 0.6. So where we're some distance m, 4 minus m, where d is greater than 4 minus m, and d is less than 4 plus m, the probability of being within that range is equal to 0.6. So I'm actually going to draw a sketch, and I think that'll help kind of determine what's going on here. So let me just move this over a little. That's fine. Okay. So kind of, I think it's a good question, but what is actually going on? So these values of 4 should give us some indication. D is some central point, and 4 minus m, and then 4 plus m. What are we actually talking about? So let's draw a bell curve here. We know our mean is equal to 4. And if we're 4 minus some distance of m, so what might that look like? So let's just say this is m right here. This point right here would be 4 minus m. So d is greater than 4 minus m. So some point d is greater than 4 minus m. And if this as well is, let's say, a distance of m, this line right here would be equal to 4.5, so what am I saying? 4.5, 4 plus m. And this last point of this 0.6, so is saying that the probability that we're within the range where d is greater than 4 minus m and d is less than 4 plus m is equal to 0.6. Or what we've seen before, this is the area or percentage under the curve. So what that means is that, and I'll keep this in blue I suppose, or red and green I guess, we're dealing with 60% or 0.6 of this standard normal curve. 60% of the values are within this range where m is some distance less than 4 and some distance above 4. Let me see if I can summarize that once again, just from the top. Standard normal curve gives us all of our values. All of the seeds are within this range, or under this curve, centered about the value of 4. If we're talking about 4 minus m and 4 plus m, these are the cutoff points where we're going to have 60% or 0.6 of all of our seeds between these two cutoff points of this range right here. So the probability that we're within this range is equal to 0.6. Alright, so that's quite a bit, and to be honest, this sketch right here would be enough for process marks, 1 process mark. How do we find this out? So we're looking for a cutoff point. We're looking for this cutoff point here, and so we can ask the calculator to sweep through a given range. And if this right here is 60%, then we know that this is a symmetrical distribution centered about the mean, and that would mean that this, oops, let me get another point, this itself would be 20%, this of course is 60%, and this would be 20% right here. And so, what are we asking the calculator to do? We're asking it to sweep through a range of 20% right here. Okay, so let's go back to the calculator screen and work this out. Menu, probability, distributions, inverse normal. The area that we want to sweep through is 0.2, mean is 4, standard deviation 0.25. Okay, and it's 3.78959. So let's go back to the document here. We know this is 3.78959. And so what did we say? If this is 4 minus m is equal to 3.78959. Essentially we're asking what is the difference between this cutoff point and this. That's what m is. M is the difference between the center value and this cutoff point. So 4 minus m is equal to 3.78959, or the distance between 3.78959 and 4. That's alternatively what we're doing here. 959, 4 minus that is just going to give us a value of 0.210. All right, that's the value of it. 0.210. Okay. Good question, kind of challenging. All right. Question 10, 8-mark question. One of the bigger questions on this paper. Here we go. A player throws a basketball. The height of the basketball is modeled by h of t is equal to negative 4.75 t squared plus 8.75 t plus 1.5. So height as a function of time. We input different values of t and we get the height at a given point. It's the height of a basketball and we're going to throw this basketball. So already we can imagine that we're going to have a quadratic, which is good. So h is the height of the basketball above the ground in meters, and t is time in seconds after it was thrown. Find how long it takes for the basketball to reach its maximum height. So we've got a function already which relates height and time. I think the most straightforward thing to do would be to graph this function and then find out these features. So let's go to the calculator screen and work this out. Let's get a new document and add a graph. So here is our function, negative 4.75, and of course we need to write t as x. So x squared plus 8.75 x plus 1.5. Negative 4.75 x squared plus 8.75. Alright, and very kind of generous question. We don't have to change any of the window at all. Let's analyze the graph and let's find its maximum. Okay. So the highest point, this is height against time. The highest point the basketball goes is 0.921. I hope this is 921 meters after 5.5. Oh no, I'm sorry. Thankfully, that's not the case. X is our time. Y is our height. After 0.921 seconds, we're 5.53 meters in the air. That's reassuring. Okay, how long it takes a basketball to reach its maximum height? 0.921 seconds. So let's go back to the document here. Part A. The question itself isn't bad, but it's a 2-mark question, so we would need to provide some kind of process. And so a sketch would be fine, and to be honest, I think that's going to be the easiest thing. So here we go. Here's our highest point, and it happens at 0.921, and that it's 5.53. And so our answer, how long it takes, 0.921 seconds. Just be careful. 2-mark question, they're going to want a sketch. Assuming that no player catches a ball, find how long it would take for the basketball to hit the ground. This is part B. And once again, we already have the graph. This is going to correspond to the point at which h is equal to 0. So 2 different ways we could work this out. I think since the graph is already open, it would be somewhat straightforward to just find this value right here, where we intersect the x-axis. But essentially we could also say, okay, if we have this function, h of t is equal to, what is it, negative 4.75 t squared plus 8.75 t plus 1.5. We can just ask, okay, well, whoops, if h is equal to 0, what is the value of t that makes this true? And then you could essentially just end solve this for t. Just be careful. End solve sometimes gives you the closest point to 0, and so it might actually give you a negative point, which doesn't make sense. That would be incorrect. We'd want to find this positive value here. Okay, I'm actually going to work it out graphically. So going back to the calculator screen, let's go Menu, Analyze Graph, and let's find the 0. Alright, after 2 seconds, the basketball has a height of 0. So let's go back to the document here. Alright, let's label the graph. This is going to be process marks 2, 0, and we might say after 2 seconds. Okay. Another player catches the basketball when it is at a height of 1.2 meters. Find the value of t when this player catches a basketball. Okay, so here we are. Here's our function once again, and I think this is a great question just to continue to solve graphically, but just to kind of show what's going on here. So here's our basketball height as a function of time. And what is going on here is there's someone who's going to catch this ball when h is equal to 1.2 meters. And so they catch this ball. We want to find the time at which this player catches a ball. So this would be a dangerous one to use end solve, because end solve would only find the first value. But it'd be unlikely for this player to catch the ball on its way up. That wouldn't make a lot of sense. So really, we're looking for this point right here. Alright, find the value of t when this player catches a basketball. There is some ambiguity. I don't think there's anything specifically in the question that says that it can't be on its way up, but it doesn't really make sense. Alright, so let's go to the document, the calculator, and let's create another function. So Menu, Graph Entry, Function, and let's put a value of f of x, or essentially just y, is equal to 1.2. Alright, and we want to find the point at which we intersect. So analyze graph, intersection, and actually we would be okay in this instance because it looks like it's negative, so that wouldn't make sense. And so we're just interested in this point right here, this 1.88. After 1.88 seconds, the ball is 1.2 meters in the air. So let's go back to the document and let's write that in. So we have a value 1.88 seconds. The basketball is 1.2 meters in the air. Okay. Find the value of t when this player catches the ball. T is equal to 1.88. You can write after 2 seconds, but all the same you can write t is equal to 2. for each of these questions as well. Okay. Part D, write down two limitations of using h of t to model the height of the basketball. So remember, h of t is actually just what we're calling this function. So what are some limitations of using this function right here to model the height of the basketball through time? So that's what h of t is, this function up here. So what are two limitations? What are two limitations? Real world question, potentially, it ignores air resistance. It ignores air resistance. Second limitation is, if we look at our models, for example, what they also do is they also consider points that occur. Our model doesn't have any, it has a value of t is greater than 0. So it doesn't deal with, let's say, negative values, which is positive, but for t greater than 0, it would assume our ball goes through the floor and so on, keeps going down. So does not consider, let's say, ball bouncing or hitting the ground. Hitting the ground. Actually, look at the mark scheme earlier, and it also has things like it assumes gravity is constant, which by and large it roughly is, or enough that, to be honest, it wouldn't be a major consideration if you're just considering a basketball flying through the air. But what it did say is that do not accept generic answers. Do not accept generic answers of generic criticisms of a mathematical model, such as there are assumptions being made or models are never accurate. So it has to be specific. All right. Okay, so really not a bad question, actually, especially if you're comfortable with the graphing calculator and graphing tool. Okay. Question 11, right here, 7 marks. Consider the function f of x is equal to 3x squared minus 5 over x, where x cannot be equal to 0. The graph of f for x is greater than 0 and less than or equal to 5 is shown on the following axes. Okay, so here's our graph. Sketch the graph of f for x is greater than or equal to negative 5 and less than 0 on the same axis. So for this function up here, they've given us part of this graph, but there's some part in this section where x is greater than or equal to negative 5 that we haven't yet graphed, and that's what they're asking you to do. So let's go ahead and work this out. This one is going to require, I think, a little familiarity with the graphing window. So let's graph this function up here, and let's put it into the calculator, and we should be able to complete this section. So let's get a new window, new document, and let's get a graph. So here's our function, 3x squared minus, and let's get a fraction, minus 5 over x. Okay, 3x squared minus 5 over x. Okay, and just returning to the document for a sec, we see we have a window where an x value has a max of 5 and a min of negative 5, and a y value of negative 60 and a max of 80. So if we want to transpose this graph or create like a mirror replica, kind of like carbon copy of this, let's get the windows the same, and it's going to help simplify things. So let's go menu, window zoom, and let's get some custom window settings. So x min was negative 5, x max was positive 5. The scale, I mean, we can put it as 1. That's going to help simplify things because it is on the graph itself a scale of 1. Y min was negative 60. y max was equal to 80, and the scale in this case was 20. That is to say, it goes up by 20s. All right, and that's going to simplify things pretty nicely, I think. Okay, so there we go. It would be helpful to find some points, so let's actually just do that. Let's find out what it goes through at, let's say, -4. So when we're at -4, we're at around 50. So I'm going to plot that in. -4, we're at about 50. And then I'm just going to do the same here. Actually, I'm just going to sweep down. Let's go trace. Let's graph trace. Let's see where we're at when we're at -2, roughly 15. -2 is roughly here. And then it might not be a bad idea to find the minimum. So when we're about at -1, we're at about 8. Okay. So that looks okay, and I'm going to try to sweep this out as best I can. So here we are, and something like that. Okay, not terrible. I mean, on the mark scheme it actually does say that it should be a smooth curve, so not broken lines, but something like this. So not broken lines, and then of course with this vertical asymptote of x is equal to 0. So where do we approach infinity? As we go up to positive infinity or down to negative infinity? This vertical asymptote, remember, happens when x is equal to 0. Okay. Sketch the graph of f on -5 to 0. Good. Write down the x-coordinate of the local minimum. That would be this point right here. And actually, going back to the calculator, we had found it already, and that was through menu, analyze graph, minimum, and there it was, once again, 0.941. So write down the x-coordinate of the local minimum. Going back to the document, x is equal to -0.941. Okay. Use your graphic display calculator to find the solutions to the equation f of x is equal to 20. Okay, so we had this original function f of x is equal to 3x squared minus 5 over x. That was this function right here. And what they're saying is find the solution for when f of x is equal to 20. And remember, equals is essentially is when f of x is 20. And so this is f of x. This is f of x, literally. But this is also f of x. 3x squared minus 5 over x. It's kind of the name that we called our function. So when is this function equal to 20? What we can do is we can substitute. Essentially, this is a question what we're asking. What are the x values here that we could put in to this equation, essentially, to get a value of 20? I think it's going to be easiest actually to graphically solve this rather than n-solve. N-solve is good if there's one solution, but if there's two or more solutions, often it's a good idea to graph. So let's go ahead and solve this graphically. So menu, graph entry, let's create a function and let's write it as equal to 20. All right, so what are the solutions? That is to say, what are the intersection points? So let's find it. So first one is going to be -2.45. So the next one, analyze graph intersection, is another one here. 0.252, and one more intersection point over here, which is equal to 2.7. Okay. Okay. So let's go back to the document and write in these values. So when x is equal to negative 2.45, and x is equal to negative 0.941, and when x is equal to 2.7. There we have our three solutions, our three intersection points. Write down the equation of the vertical asymptote for the graph. So C, remember vertical asymptote essentially is a line that we approach but never reach. So vertical asymptote in this case, or in all cases really, is a line that you approach but never reach. And this would be your vertical asymptote in this case, the line where x is equal to 0. Here it is, this line that we approach but never reach, the line that we come close to. Remember, horizontal asymptotes in this case would be on the horizontal axis. What do we approach but never reach? Well, in this case it would be y is equal to 0. So vertical asymptote occurs when x is equal to 0. And lastly, they're asking us to write this as an equation. So please do not forget the equal sign. X is equal to 0 for for vertical lines. Let me just show one other example really quick. If we had some equation which was shifted over just slightly, so let's say it looked like this, and then like this, and the vertical asymptote was, let me change this just slightly, and the vertical asymptote was right here, so this line that we approach but never reach, this would be x is, let's say, equal to 2, if this point right here was 2, for example, and so on. So vertical lines have this equation, x is equal to 2, and if we're considering horizontal asymptotes, so let's say there's a parachute jumper, and they jump out of this plane, and this is their velocity, and initially it's 0, and then they reach some kind of terminal velocity, but they never actually reach this value. This would be our horizontal asymptote, and it would be y is equal to, let's say, I don't know, 20 meters per second or so, something like that. So this is horizontal, has this y value. Y is equal to 20. All right, and 12, not sure how many questions are left. 2 more questions? 2 more questions, okay. All right, so these should be getting more challenging now. All right, 5 mark question. In a game, balls are thrown to hit a target. The random variable x is the number of times the target is hit in 5 attempts. The probability distribution for x is shown in the following table. Find the value of k. So part A, asking us to find the value of k. So probability distribution, what does that mean? We're throwing a ball at a target. X is the number of times the target is hit in 5 attempts. So x is number of times the target is hit. So what are we saying? There is a 15% chance that the target is hit 0 times, 20% chance that the target is hit 1 time, k% chance that it's hit 2 times, 0.16 or 16%, 2k that it's hit 4, and then a 25% chance that we hit 5 targets on 5 attempts. So hit the target 5 times on 5 attempts. So find the value of k. So what do we know? We know that the total sum of all probabilities has to equal 1. That is to say, one of these things has to happen. We're going to hit we're going to hit 0 target, 1 target, 2, 3, 4, or 5 targets. These are the only things that can happen. And if we were to sum up all the possible things that can happen, knowing that one of these things has to happen, it would equal 1.00, or essentially 100%. probability of all of these discrete events, knowing that one of these things has to happen. If we sum it together, it should equal 100%. So, or just a value of 1. So let's go ahead and write that out. So we have 0.15 plus 0.2 plus k plus 0.16 plus 2k plus 0.25. We know that this should all equal 1. So after we have some equation, let's go ahead and end solve. And you actually don't need to write end solve on your paper, just the equation is fine. I do it just to kind of show what we're doing here. Okay, so let's go into the calculator and write this out. Menu, algebra, numerical solve. 0.15 plus 0.2 plus k plus 0.16 plus 2k plus 0.25 equals 1. Remember last time it didn't really accept that too well, so I'm going to write 2 times k and then telling the calculator what to solve for. Okay, k is equal to 0.08. Okay, going back to the document here. K is equal to 0.08. The player has a chance to win money based on how many times they hit the target. The gain for the player in dollars is shown in the following table, where a negative gain means that the player loses money. Okay. Here's our table. Determine whether this game is fair. Justify your answer. Okay, so we hit 0 targets, we lose $4. 1 target, we lose 3. 2, we lose $1. 3, it's a tie. We don't win or lose money. We hit 4 targets, we win 1, and we hit 5 targets, we actually get $4. We can't just simply add these up because there's actually a greater probability of some of these things happening compared to others. So in this case, there's a 25% chance that we actually hit all 5 targets. So being able to win $4 in this instance, where we have what is overall a pretty likely event, is something that's quite positive in terms of us winning money. And in this case, although we lose $4 in this instance, this only happens 15% of the time, so it might not be, let's say, as significant. So probability does matter. The probability or likelihood of each of these events will matter. So we have our formula for expected outcomes as just the earnings of -4 times the probability of occurrence. So expected winnings should equal expected losses, and in that sense, a fair game has an overall expected return equal to 0. That is to say, you don't win and you don't lose. In this case, the expected return is equal to 0. So let's write this out. For part B, we have a 15% chance of losing $4 and a 20% chance of losing $3. And K we found out was 0.08, so we have an 8% chance, or 0.08 chance of losing $1. 16% chance of coming out even, I guess. 4, whoops, let's rearrange this. 0.08 times 2 would be 0.16% chance of, in this case, gaining $1. And lastly, 25% chance of winning 4 points. And if we sum all of this up, this would be our expected return, our expected winnings or losses. And if this equals 0, then the game is fair. So let's add this up on the calculator. So 0.15 times -4 plus 0.2 times -3 plus 0.08 times -1 plus 0.16 times 0, I guess that one wasn't so necessary. 0.16 times 1 And then lastly, 0.25 times 4. So actually just going to make sure that all of this is incorrectly rather. Good. Alright, and the value is actually equal to negative 0.12. So on average, it looks like we would expect to lose 12 cents for every game. So determine whether this game is fair. So back at our document here, we see that the expected return is equal to negative 0.12. So the game is not fair. There's not an equal chance of winning and losing. Fair game, we would expect to have an expected return of 0. Okay, that's it. Okay, 9-mark question to end things off. An engineer wants to calculate the cross-sectional area of a dam. The cross-section of the dam can be modeled by a curve and 2 straight lines as shown in the following diagram, where distances are measured in meters. So he wants to find the area under the curve here. So this curve right here wants to find the area underneath. The curve is modeled by a function f of x. The following table gives values of f of x for different values of x in the interval between 0 and 3. So just for this interval from 0 to 3, where x is greater than 0 and less than 3, so this part only. Okay. Calculate an estimate for the area in the interval of 0, where x is greater than or equal to 0 and less than or equal to 3, by using the trapezoidal rule with 3 equal intervals. Okay, so 3 equal intervals. There was another paper where I kind of went over more in-depth kind of explanation of the trapezoid rule. We'll bring the trapezoid rule up here, and let's look at it in the formula booklet. So let's go. This is going to be under calculus. So calculus, topic 5. Here we go. And there we have it actually. 5.8, the trapezoid rule. What is this saying? This is the sum of the area under the curve. This is our lower bound and our upper bound of some function. And then here, we'll go into the next screen. I'll write this out and we'll actually go over this again. And I'll show you what this means. But there it is. We do have the trapezoid rule, of course, in the formula booklet. Okay, so I'm going to write this out. I'll write it down here. So we're looking for the area under the curve. So that's what this means essentially, the area under the curve. And we have some starting point and some ending point of some function. And I think they gave us the function somewhere. They did. No, they didn't actually. They just gave us the derivative. So in this case, we don't know the function, but we have the intervals. And the trapezoid rule looks like this. 1/2 h, which we can find, and then open up some brackets. y0 plus yn plus 2 times y1 plus y2 plus, and these are all of the intermediate values, all the way up to yn minus 1. So right up before the second last one. So this yn is the height or the y value, let's say the y value at the final y value, or at the end of our interval. So let's say final, essentially y value, often the height, final y value. y0 is our first y value, and these of course are our intermediate y values. And then of course we have this other variable here, this h, and in the formula booklet they give us this h is equal to b minus a over n. And earlier when we talked about this area right here, and we said, okay, this is the starting point and this is the end point, so this is the end and this is the start, This h just refers to the size of the intervals. So in this case, we know that there are 3 equal intervals between 0 and 3. So h is going to equal to 3 minus 0, endpoint, starting point, broken down into 3 equal intervals, and it should be equal to 1. So let's go and put this in here. So 1/2, the size of our intervals are equal to 1. The first y value when x is equal to 0 is equal to 3. The last y value when x is equal to 0, or sorry, when x is equal to 3 is equal to 42, plus 2 times, and then these are all of our intermediate values. But at this point, since we're just having, this is probably why it's the second last question, they've given us more information that we need. We're only breaking this area under the curve into 1, 2, and then 3 trapezoids right here. Only into 3 trapezoids. So we're really only concerned with, this is y0, this is y1, this is y2, and this is y3. So we're only concerned with the 0, the first, the second, and the third value. So kind of trying to confuse, potentially asking for a little more detail, not a straightforward question. Intermediate value is going to be 8. At 2, it's going to be 19. And then the final value is actually, we don't have it. We just have these 2 values, really. And then let's close the brackets. So let's work that out on the calculator. That's our trapezoid rule. So let's get a new screen, actually. Okay. 1/2 times 1, or we can just leave that actually. Let's open up 2 pair of brackets, 3 plus 42 plus, and then we wanted to multiply these other values by 2. 8 plus 19. And just make sure that you have these brackets. So we have 3 plus 42 plus 2 times 8 plus 19, and all of these are within these bigger brackets. So we're saying order of operations. We want to take 3 plus 42, add that together, then take 2 times 8 plus 19, add these 2 things together, and then we want to multiply all of that by half. So just be mindful when you are typing this in. To be honest, might be a good idea to just write 8 plus 19 times 2 plus 3 plus 42, and then multiply everything by a half. So we've got 99 over 2, or just as a decimal, well, it's going to be 44.5. Convert to decimal, there it is. Sorry, 49.5 rather. Okay, so let's go back to the document. 49.5. That's our area under the curve. Just to give a quick demonstration, really quick, because I know I've done this in another video. Area of a trapezoid, and this is given to you in the formula booklet, is a plus b over 2 times the height. So if we have some trapezoid like this, and it's on its side, a and b would just be the lengths of these parallel sides, a and b, and then h would be the height of the trapezoid. What we're doing when we're doing the trapezoid rule is we're just rotating these trapezoids on the side, and this of course now becomes h. Right? These 2 things correspond to each other, and then this shorter side is a and this longer side is b. And so if you wanted to, in this case, I'll use a different color. We know that the height of this is 3. When we're at 1, the height is equal to 8. And when we're at 2, the height is equal to 19. And when we're at 3, the height is equal to 42. If you wanted to, we could just find A1, A2, and A3, just like that. And so it would be what? 3 plus 8 over 2 times the height, which is just equal to 1. And then this, of course, is going to be 8 plus 19. 8 plus 19 over 2 times the height of 1 again. And this last one right here, 19 and 42. 19 plus 42 over 2, and then times the height of the trapezoid is 1. And if you take all of these areas, you will get this area under the curve. That's exactly what the trapezoid is doing, the trapezoid rule. It's creating trapezoids and using these to approximate the area under the curve. Okay, so 2-mark question for trapezoid rule. It looks like not that much actually, usually it's 3 marks. Here it is, trapezoid rule. Size of our intervals, that is to say, if we're breaking this up into 3 portions, from 0 to 3, size is just equal to 1. And then first y value, last y value, and 2 times all the intermediate y values. In this case, we're dealing with points 0, 1, 2, and 3. Okay, 4-mark question coming up. I'd imagine it's quite challenging. It is known that f prime of x is equal to 3x squared plus 4 in the domain of x is greater than 0 and less than 3. So we have this function here, which is given by f of x. The derivative of this function between these values where x is greater than 3 and less, x is greater than 0 and less than 3 is equal to 3x squared plus 4. Find an expression for f of x in the domain of x is greater than 0 and less than 3. That's a great question. To be honest, I really like this question. It's very nice. Okay, so let's write down some information. So we have f prime of x, and we know f prime of x is 3x squared plus 4. Very cool question, I think. 3x squared plus 4. All right. So f prime of x, our derivative is equal to 3x squared plus 4. And what they want us to do is they want us to find f of x. So it's kind of interesting. Often we're given f of x and who knows, some f of x. And we're saying, the question that we often get is, okay, well, take the derivative, find the derivative. And for example, I'll write this out here. This is our rule for the derivative. F of x is equal to x to the n. And then what does that mean? That means our derivative, what happens? We multiply by n, and then our exponent, of course, decreases by 1. So we take this n, multiply it out in front. Here it is, and then the exponent used to be n. Now it's n minus 1. It's 1 less. Okay. And this is what's called taking the derivative. That's our derivative. And what we want to do in this case is we want to take the antiderivative. We want to take the antiderivative. We want to go the other way. And so what does that mean? I'm going to write it out in a different color here. And this is given to you in the formula booklet, but just to explain it as well. If f prime of x is equal to x to the n, then f of x, if we're going the other way now, and we're taking the antiderivative, what is that going to mean? Well, it would mean that originally our exponent would have 1 more, right? So if we're going down this way and we're taking the derivative, we would subtract our exponent by 1, and we would also multiply our exponent by whatever, or multiply our term by whatever that exponent was. So in that case, we would want to also divide by whatever that no exponent is. Essentially, the idea is, if this was our original expression, f of x, if we were to have taken the exponent and multiplied it out in front, we would have n plus 1 times x And to undo that process, we know our exponent is going to have a value of 1 more than it otherwise would, and we're going to want to divide by whatever value that exponent is, because we know when we take the derivative we multiply that value, and to do the opposite would be to divide by it. Let's actually look at this in the formula booklet. Here we go. Calculus. There it is. So 5.5, the integral of x to the n is n plus 1 over n plus 1 plus c plus c plus c, that unknown constant. Okay, so let's work it out. So I'm actually going to rearrange this somewhat. Sometimes I think it's a little better looking at things sequentially this way. So here is f of x, or f prime of x. This is our derivative. Let's take the antiderivative. So we know that if our derivative is to the power of 2, then our original function would have been to the power of 3. And what we would have done if we would have taken the derivative at this point is we would have multiplied it by 3. So we can imagine actually just doing this in reverse. If we were to multiply it by 3, we'd actually get this 3x squared. So we are kind of done. But to follow the process as it is, we could just write out 3x, increase the exponent by 1, but then also make sure that we're dividing by this same value. So just to show you that in more detail, increase the exponent by 1, but then also divide out by that value. And here we have plus 4. We know that the only way to get a value in a constant when we take the derivative is for there to be a 4x, because if it was just a plain constant, it would have disappeared. And in this case, we don't know, the last part of this is we don't know if there was an originally some constant in this equation, or in this original function. So we would put this unknown value of some constant at the end. So let's clean this up a little. F of x is equal to 3 over 3 just becomes x cubed plus 4x plus c. I'm going to make a little more room for this and bring it down just once. Okay, and then lastly, to be honest, I actually think this is quite a good idea, is just derive this. Find out what fx prime would be, and it would be 3x squared plus 4, and that would be it. And that's exactly what we have here. And to be honest, that should be some good reassurance. Whatever your integral is, your antiderivative, derive it and see if you get back to what you originally had when you were given the derivative. Okay, so why is this a 4-mark question? We need to find out what the value of c is. We have a point on a line of this function. We can choose any one really. We have 0, 3, 1, 8, and 219 or 342. 0, 3 is probably going to be the easiest, so let's use that. When x is equal to 0, y is equal to 3. So y is equal to 3 when x is equal to 0, and everything with a 0 is just going to go away. And so we have 3 is equal to c, or c is equal to 3, and our derivative, sorry, our antiderivative is x cubed plus 4x plus 3. So we found out that c was equal to 3. Nice question, I think. Okay, hence find the actual area of the entire cross-section. All right, actual area of the entire cross-section. Interesting question, kind of a lot going on here. I'm going to erase some of this right here. Okay, there we go. Okay, so the actual area of the entire cross-section. The area can be represented in a few parts. We have this part right here. So this part, which we can call A1, I suppose. And then we have this part right here, which we could call A2. And then lastly, if we wanted, we have this part right here, which if we wanted, we could call A3. So for this part right here, we use the trapezoid rule, but we don't need to use the trapezoid rule right now because we have the actual function itself. So how do we find the area under the curve? If we have the function itself, we can just use our integral. So let's take the integral of our function, which was x cubed plus 4x plus 3. X cubed plus 4x plus 3. And then it's in terms of dx. And then of course we had these lower bounds and upper bound right here. So our starting value, we want to start at 0 and we want to end at 3. And so essentially what this says is find the area under the curve. Find the area under the curve for this function starting at 0 and going to 3, and then always just with the same variable here. So since it's in terms of x, we write it in terms of dx. So let's go ahead and work that out on the calculator. Alright, so menu, let's go in to calculus, here we are, and let's take numerical integration right here. We wanted to start at 0 and go to 3, so our lower bound and upper bound. Our function itself was x cubed plus 4x plus 3, x cubed plus 4x plus 3, and since it's in terms of x, we write this just as dx. There we go, 47.25. So let's go back to the document and let's write in a1 is equal to 47.25. Alright, a2 right here is just a rectangle actually with a base of 1 and a height of, okay, so let's use this. So what is the height when x is equal to 3? It's equal to 42. So when x is equal to 3, y is equal to 42. So it has a height of 42. So length times width is just going to be 1 times 42. A2 has a height of 42. And A3 is a triangle. And so the area of a triangle, A3, is going to be equal to base times height over 2. So what is our base? If we're going from 4 to 6, our base is equal to 2. Oops. Base is equal to 2 times, and our height, once again, we don't have a value for, but it's a straight line right here. So if this was a y value of 42, this is also going to be 42. So right here, 42 once again. So base times height divided by 2, and these 2's are actually going to cancel out and we're just going to be left with 42. Okay, so here we go. The total area, let's write it out here. Total area is going to be given by, we can write A1 plus A2, A3. I'm not going to use the colors here. A1 plus A2 plus A3. A1 we found out was 47.25. A2 was equal to 42. And A3 was also equal to 42. So adding all that's up, I'm going to do that out on my calculator right here. It equals 131.25. So I really wouldn't recommend this kind of ordering. It's a very disorganized process. Just kind of running out of space here. That's why I wrote it like that. So this is 131. So A1 plus A2 is equal to this, which is equal to this, which to 3 sig figs is equal to 131. Okay, that's at least a little better. Okay, and that is our actual area of the entire cross-section, 131 centimeters in this case, or meters, I suppose. 131 square units in either case. Okay, and I think that was the final question. Alright everybody, I hope that was helpful, and as always, best of luck. Bye-bye.